In the summer of 1977, NASA's Jet Propulsion Laboratory launched two Titan Centaur rockets, each carrying a nearly identical spacecraft, Voyager 1 and Voyager 2. Designed to last just 5 years, these twin probes were initially tasked with studying Jupiter, Saturn, and their major moons. Remarkably, nearly 45 years later, NASA remains in regular contact with both probes, which continue to receive commands and send back data to Earth's deep space network. This makes Voyager the longest-running space exploration mission in history. Within 4 years, the probes completed their original objectives, prompting NASA to extend their mission to include Uranus and Neptune. Eventually, they embarked on the ambitious Voyager Interstellar mission, aimed at exploring the farthest edges of the Sun's influence and beyond. Today, Voyager 1 and Voyager 2 have traveled an astounding 22 billion and 18 billion kilometers from Earth, respectively, venturing beyond the heliosphere into interstellar space. However, even for these enduring explorers, time is running out. As early as 2025, the Voyager probes may lose their remaining power supply and fall silent forever. In preparation, NASA has begun shutting down the probe's instruments one by one, hoping to extend the mission's lifespan by a few more years. When the probes finally go dark, they will leave behind an extraordinary legacy, a treasure trove of data unmatched in its scale and significance. Now, as we approach the final chapter of the Voyager mission, we ask, what did Voyagers 1 and 2 uncover on their incredible journey? How well did their instruments endure the challenges of interstellar travel? And why have NASA scientists been so astonished by the discoveries made along the way? This is the story of the most remarkable findings from the nearly 45-year Voyager mission. It's a chance to relive the extraordinary journey these probes embarked on after leaving Neptune's orbit, traversing the icy outer giants of the solar system and venturing to the very edge of interstellar space. Originally designed for a 5-year mission, Voyagers 1 and 2 endured far longer thanks to visionary design choices made by their team of scientists and engineers. Each probe was equipped with a radioisotope thermoelectric generator, converting heat from the decaying plutonium-238 isotope into electrical power. To ensure durability, the probes featured redundant systems for most of their 11 scientific instruments and 16 hydrazine thrusters, including 8 backups. Timing also played a critical role. When the Voyager mission launched in 1977, NASA capitalized on a rare planetary alignment that occurs once every 176 years. This alignment allowed the probes to perform flybys of Uranus and Neptune with minimal course adjustments while receiving gravitational assists from the planets they passed. These boosts increased their velocity, propelling the probes farther than anyone could have imagined. At the time, relying on more than just rocket propulsion was a relatively new concept, previously attempted only during NASA's Pioneer missions to Jupiter and Saturn. In 1981, Voyager 1 broke free of the ecliptic, the plane of Earth's orbit around the Sun, heading 35 degrees north. Voyager 2 later veered 48 degrees south, moving below the ecliptic. Once the Voyager planetary mission transitioned into the Voyager interstellar mission, both probes had their cameras deactivated to conserve power. Voyager 1's last photograph, the iconic pale blue dot, captured Earth from a staggering distance of 6 billion kilometers, making it the farthest image of our planet ever taken. Yet, this marked only the beginning of their epic journeys. To reach interstellar space, the Voyagers first had to cross the termination shock, a turbulent region where hypersonic solar winds clash with the interstellar wind. Beyond that lay the heliosheath, a zone where slowing solar winds compress, becoming hotter and denser, before finally encountering the heliopause, the outermost boundary of the heliosphere and the gateway to interstellar space. But contrary to popular belief, entering the interstellar medium does not signify the end of our solar system. In fact, it will take another 300 years for Voyager 1 to reach the Oort cloud. The Oort cloud is a massive region of icy planetesimals surrounding our solar system, resembling a protective bubble. It will take the Voyager probes another 30,000 years to fully exit the cloud and leave our solar system behind. During their journey through the heliosheath, the Voyagers made an astounding discovery. The Sun's magnetic field spins in opposite directions at its north and south poles, creating a ripple effect where the fields meet, known as the heliospheric current sheet. This is similar to the rings formed when a stone is dropped into water. But when this current sheet reaches the termination shock, it compresses, much like ripples hitting the edge of a pool. After passing the shock, the Voyagers observed that the accumulated ripples form magnetic bubbles. This revelation shows that the boundary of the heliosheath is far from the smooth, well-defined edge scientists once believed. Instead, it's a dynamic and magnetically active environment, prompting a complete overhaul of our understanding of the heliosheath. On July 25, 2012, the Voyager 1 space probe made history as the first man-made object to leave the Sun's heliosphere and enter interstellar space. It was traveling at an astonishing speed of 540 million kilometers per year, or 3.6 astronomical units, AU, with 1 AU being the distance from Earth to the Sun, roughly 149.6 million kilometers. Voyager 1 crossed the heliopause, the boundary where the Sun's influence ends, at a distance of about 120 Australian dollars from the Sun. This was a significant discovery in itself, as the exact location of the heliopause had been uncertain. Some early models suggested it might be as close as Jupiter, while others placed it much farther. The heliopause marks the point where the Sun's solar wind, a continuous flow of charged particles like electrons, protons, and alpha particles, collides with the interstellar medium, which consists of gases, charged particles, and cosmic dust from the Big Bang and ancient supernovae. This collision of two powerful streams creates a boundary of equilibrium, known as the heliopause. At first, NASA wasn't certain whether Voyager 1 had actually crossed the heliopause and entered interstellar space. As expected, the probe's plasma wave detector registered a huge surge in plasma density, 80 times higher than what it had observed in the outer heliosheath, and a notable increase in galactic cosmic rays. However, something odd occurred that left scientists puzzled. After crossing the heliopause, Voyager 1 didn't detect any change in the surrounding magnetic field. This was unexpected. Theoretical models predicted that the magnetic orientation would shift in an area dominated by the magnetic fields of other stars. But surprisingly, Voyager 1 found no noticeable change in the surrounding magnetism. NASA was so perplexed that they waited almost a year before confirming that Voyager 1 had indeed entered interstellar space. On November 5, 2018, Voyager 2, traveling at a slightly slower pace of 490 million kilometers, or 3.3 astronomical units, per year, joined Voyager 1 as the second human-made object to reach interstellar space. This milestone occurred 120 astronomical units from the Sun, and, just like Voyager 1 did 6 years earlier, the probe found no change in the surrounding magnetic field. However, scientists were surprised by another discovery. The Sun follows an 11-year solar cycle, during which its activity increases and decreases. Voyager 2 crossed into interstellar space during a period of peak solar wind activity. Models had predicted that the size of the heliosphere would change with the solar cycle, expecting it to expand when Voyager 2 made its crossing. But, Voyager 2 passed the heliopause at the exact same distance as Voyager 1 had 6 years earlier, indicating that our models were incorrect. This discovery, along with the magnetometer finding, highlights the importance of validating theoretical models with real data. It now appears that the boundary between the heliosphere and the interstellar medium is far more complex and fluctuating than previous models had suggested. One prominent theory suggests that our Sun formed billions of years ago from a hot, ionized region created by the explosion of one or more supernovae, with magnetic turbulence still affecting the area near the heliopause. As the probes continue their journey into deeper space, they will likely encounter a shift in magnetic orientation. However, by that point, their instruments will probably no longer be operational. While the iconic Voyager mission is nearing its end, the twin spacecraft are just beginning their epic journeys across the cosmos. In about 40,000 years, Voyager 1 will likely drift toward AC plus 793888, a star in the Camelopardalis constellation, while Voyager 2 will come within 1.7 light-years of the star Ross 248.